All right, hail and well met. It's your friendly neighborhood professor here, ready with another lecture, jam-packed with statistical goodness. And for this particular lecture, as we can see, we'll be talking about credit risk analytics. So what are credit risk analytics? So credit risk analytics is essentially studying, analyzing the riskiness, the inherent riskiness of extending credit to an applicant. Generally speaking, probably the most widely used context is big banks trying to decide whether or not to extend a loan or a credit card to a customer. Although it certainly can be used to generalize to any number of reasonably similar situations. We're going to focus on this pretty cool data set. Should be posted on D2L, so I encourage you to, in addition to listening to this lecture, actually download that data set and play around with it a little bit. It contains the characteristics and delinquency information. So delinquency means, essentially not paying back the loan for 5,960 home equity loans. So almost 6,000 loans. A home equity loan is essentially a loan that somebody takes out, and the collateral, so a lot of times loans have collateral. If the person doesn't pay it back, then you get something from them. And in the case of a home equity loan, it's the equity of a house, right? So these loans are given to homeowners. So maybe that maybe makes it a little less risky right there. We already know the person owns their own home. And then we have this collateral as well, right? A home's equity is essentially just the difference between the amount of the loan on their mortgage, the difference in the amount of the loan on their mortgage, and how much that house is currently worth. So the primary variable of interest, this is historical data. So these are sort of old loans, recent loans. And for all of them, we know basically whether or not that loan was paid back. And so the variable that records that information is labeled bad, bad loan. And it's 1 if the applicant defaulted, so it's very directly measuring whether the loan went bad or not. 0 if the loan was paid back, right? So this whole idea of bad and good is pretty commonly used industry jargon, particularly in this sort of field of credit risk analytics. And I don't know about you, but I find it actually quite refreshing to have some very simply coined jargon, right? Much whoever came up with the phrase homoscedasticity could have learned a little something from this in naming simplicity. So here are the variables in the data set. There's quite a few of them, right? There's I'll let you read through them. You can pause the video and kind of look it over. But right, there's the amount of the loan, how much was due on the mortgage, right? So remember, this is a home equity loan, so it's given to people that own homes. What's the value of that current property? What was the reason that they took the debt or took the loan? And here we have 2 possible reasons. Their jobs, how long they've been at their jobs, number of major derogatory reports, number of delinquent credit lines, et cetera, et cetera. So I'm going to keep this pretty simple. I say simple, but I actually feel like it still will be a lot. Sometimes these lectures can be challenging. I know technically they're supposed to be on the longer side, but I tend to try to measure it not so much on like pure length, but just how much knowledge is being sort of shoved into your brain, because at some point our brains are just going to shut down. And so the two the two most widely used strategies, like big picture for a process like this, right? I have this y variable, this response variable, this dependent variable that's essentially binary, right? It's the person, they paid back their loan or they didn't pay back their loan, right? So that's called binary. Sometimes it's called dichotomous. If we wanted to go with that naming simplicity, we could call it just takes two values. And we want to know, like, okay, so I have this outcome, a person pays back their loan or doesn't pay back the loan, and I have a bunch of other variables, right? Which of these other variables is useful in terms of me trying to determine whether the person will pay back the loan or not? Because if I know that, right, then I can make a decision on whether I think it's worth it to give this person a loan, or right, a person that has similar demographic information. Or is it maybe too risky and I don't want to extend that loan? And so sort of like the two big kind of statistical techniques that are best adapted for this type of statistical quandary is logistic regression and decision trees. So I'm going to focus in the next few slides, maybe next like 15-ish slides, talking about logistic regression. Some of you have taken Stat 507. In Stat 507, we spend like 3 or 4 weeks really digging into logistic regression. It's a powerful statistical technique. Its uses extend well beyond the field of credit risk analytics. However, the majority of you have not taken Stat 507. And so because of that, I am going to spend some slides talking about it like big picture. Obviously, we can go into a lot more depth. You will, when you take Stat 507, learn logistic regression with a lot more depth. And then after that, maybe you could revisit, right, some of the stuff that we're talking about right now with a more experienced eye. So logistic regression, we'll talk about that in a slide. The other approach is something called decision trees. So decision trees is kind of like a classification system where you make these kind of like branching paths that visually or graphically end up looking like a, I don't know, like kind of like a generic Christmas tree. You know, so kind of the idea is you would say like, all right, if the person makes this much money, then move them into this category, move to the right category. If they make less than that, move to the left category. And then like now you look at the right category. These are the people that made a lot of money. And you say, all right, like if this person has a good credit history, move them to the right. And now maybe moving them to the right is like moving them into the category of good. That is someone that we think would pay back the loan. If they have a bad credit history, we move them to the left where, you know, we would characterize them as bad, someone that we don't think we should extend a loan to. I really went back and forth. I opted not to go into decision trees for a few different reasons. In the context of credit risk analytics, logistic regression is used like 99% of the time, and decision trees is used not at all, or in a very small sort of supplementary role. So even though decision trees are widely used in certain contexts, they're just not really in this particular context. The other reason is that our version of SAS like doesn't really do decision trees. It doesn't really have a proc that can handle it. There's like a SAS extension called Enterprise Miner, and if you end up working at a company that uses SAS for this type of stuff, they'll have Enterprise Miner, but our university does not. An Enterprise Miner can do these decision trees very easily. Alternatively, right, you can do them in R, although even in R, it's like takes a little bit of work. But I know not everyone has experience with R, so you know it just felt like an unnecessary deviation. I am putting it out there. I think it's nice to be aware of decision trees are kind of this like alternative classification system. They kind of fall into this like data mining umbrella, and you do see them in like job postings a lot. Just not for this type of context. All right, so back to logistic regression. Logistic regression, pretty similar to regression from Stat 512. The key difference is that, right, instead of this y numeric variable, our y is now this binary variable. So we're modeling y, this yes or no, this good or bad, and right, I am simplifying it because technically those of us that have had Stat 507 know that we're actually technically modeling the log odds of a binary variable. But from a conceptual standpoint, we can think of it as just modeling yes or no as this linear function of predictor variables, right? So it's our right-hand side has that very familiar framework, that beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. We can use logistic regression in SAS very easily. SAS has fantastic functionality when it comes to implementing logistic regression, and we can do it in SAS using ProcLogistic. So here's some pretty standard code for ProcLogistic. So right, ProcLogistic, I put the descending option. I'll talk in a second why I put that descending option there. You don't, not every code will have that, but our code, our example needs that. There's a class statement and a model statement, and we end our code with the run statement. So the model statement should be pretty familiar to us. Our y variable goes on the left, our x or explanatory variables go on the right. We can put interaction terms in there and really do most of the stuff that we were able to do in Stat 512. Any variable in the model statement that is categorical, we need to put in the class statement, right? Class for like classification. It's a classification variable. So, right, in our example, we had like the reason the person took out the loan was a categorical variable, and their job was a categorical variable. I think we talked about the class statement at the very, very, very end of Stat 512. So anything that's categorical needs to go up there. I do slash param equals ref. Ref is for reference. So in Stat 512, we talked about like when you have a categorical variable, you essentially have to like break it into like a number of dummy variables, right? If my categorical variable has k categories, I make k minus 1 dummy variables. And we talked about how you can do that with these kind of 0, 1 dummy variables. That's called reference coding, right? Because we sort of pick a category to be omitted, and we think of that as our reference category. It should be pointed out that that's not the only way to do it. And ProcLogistic by default uses a different way. It's not like one way is better or worse than the other. It's like two different ways of writing or expressing the same thing. Both ways will kind of like come together with the same results. But based on what we've seen in Stat 512, the reference parameterization is going to be more familiar to us, so I specified that. And then the descending option. So in this case, we want to model whether or not the loan is bad, whether or not the person is going to default. That's what we want to know. Will the person default, yes or no? Based off SAS defaults, if I didn't ask SAS to do it otherwise, SAS is going to model the outcome 0 rather than the outcome 1. It's going to model by default the smallest option. So in our example, it would model the outcome of bad equaling 0, which is actually modeling the probability, the likelihood of something being good, which is the opposite of what we want. So I override that default. One of the ways I can override that default is with that descending option. The descending option reverses like the order that SAS uses. Instead of ascending, it's now using descending. And in the process, it now models the outcome 1 rather than the outcome 0. Yeah. It is a big deal, right? It sounds a little bit like semantics, but you have to know like what you're modeling, right? Because if you're accidentally modeling the opposite of what you say, and you say like you build this whole model and you like turn it into like your boss, and you tell your boss like, oh yeah, this person wants like a multi-billion-dollar loan. Well, guess what? I just calculated that the probability of them defaulting on the loan is like less than 0.01%. But what if instead you actually modeled the opposite of what you thought you did? So, right, you thought that the probability you're handing your boss is the probability of defaulting, but it turns out you're handing your boss the probability of them actually like paying back the loan. And so you're telling your boss like, yeah, there's like an almost 0% chance that the person will default, so give them the loan, but the reality is that is almost a 0% chance that they will actually pay back the loan. That's a big oops, right? So, I mean, like this idea of making sure that we're modeling this thing correctly, in my very humble opinion, is maybe like the most important thing we need to confirm when we're running our code. Otherwise, I think everything up here we already talked about on the previous slide. Ooh, sorry about that. Got my heart rate up. Got a little too passionate. Common problem when discussing statistics. All right, so here is our output from ProcLogistic. I'll go over some of it. So notice it says that 1,172 observations were deleted. So there is a lot of missingness in our data. That can be a common problem. There are some ways of working around it, but ProcLogistic by default just will not use any observation for which it's missing information. Notice I have the response profile section. So that tells me that, right, of the remaining data, I have 924 people who did not pay back their loans. I have 3,864 who did pay back their loans. So, right, that's pretty common in these types of data sets that, right, the rarer outcome is defaulting, right, because in general people do pay back their loans. So it's nice to hear about human beings. And then notice underneath that it says the probability modeled is bad equals 1. If you want to play around with this code, right, the data set's posted, try running ProcLogistic without that descending option, and you will see that it says probability modeled is bad equals 0. So to me, the very first step when I run ProcLogistic is I look at that line, probability modeled is what? To make sure that SAS is doing what I want it to do. It is modeling the correct outcome, not the opposite of the correct outcome. That class level information is basically just saying, it's basically telling us, because again, right, when we use that class statement, it saves us from having to like build those dummy variables ourselves, which is something that we did do in the earlier stages of Stat 512. Using the class statement, we don't have to do that, but it doesn't mean it's not being done. It's just SAS is doing it for us. And so this is basically SAS is telling us like how it made the dummy variables. And it may or may not be the way we want it to do it. There are options within ProcLogistic where we can change how it defined these dummy variables. But right, the reason category only had two possibilities, so it essentially made one dummy variable. That one dummy variable was a 1 if the person took their loan out for a debt consolidation. It was a 0 if they took it out for home improvement. The job category has 6 outcomes. Right? You have a managerial job, an office job, you're a professional executive, you have a sales job, you're self-employed, or other. So 6 categories. That means that we need 5 dummy variables, right? And I can see there's 5 columns. Each column is a dummy variable. So that first column is basically, is the person a manager, yes or no? The second column is the person like in an office job, yes or no? The third column is, does the person have an other job, yes or no? So the way that SAS set this up, I don't want to say we, because really we didn't do anything. SAS just used its sort of pre-existing defaults and basically assigned the last category, alphabetically speaking, to be the reference category. So SAS set self-employed as the reference category. We have these model fit statistics. I won't get too much into those, but we have seen them in our class, right? We have the IC there. That SC is the BIC. That's the Schwarz-Bayesian criteria. So I have my IC and my BIC. And then I have a third line, which is the -2 log likelihood, that's actually the one that's used probably more often in a logistic regression context. But it's a little much for getting into right now. It's just like a big picture overview. We have our global tests. There's 3 different ones. I forget. One is recommended over the others in most situations. I'm not good at remembering which one because they pretty much all always agree in every real life data set I've used. But they're essentially saying, right, is at least one of the variables in my model significant, yes or no? And so here, all 3 of them are highly significant, indicating that at least one of the variables that I put into my model. Oh, and I didn't highlight, but if you go back and look at my code, right, I only use like maybe half the variables from our model for this introductory example, just to kind of keep things simple. I just took the first half. I didn't put a lot of thought into it. But it's saying at least one of those variables is significant. Which one or which ones? Well, I would have to dig deeper to find out. Part of that digging deeper is to look at that type 3 analysis of effects. So I can see that the loan variable, how much the loan was for, is highly significant. How much is still due on their mortgage is non-significant. Value of their home is non-significant. The reason for the loan is non-significant. Their job category is highly significant. And how long they've worked at their job is highly significant, right? Now, keep in mind, these are, it says type 3, these are type 3 p-values. So it's basically saying, right, if I look at loan, it's saying that loan is significant above and beyond the contribution of all the other variables. So based on the information presented, right, the next step would be what? We would probably be implementing a backwards modeling approach. So we would remove the variable with the largest p-value, right? So in this case, we would remove the value variable and we would rerun our model. I'll talk about some easier ways of doing that in a few slides. And then it got a little bit cut off, but underneath that is essentially our model equation. And I'm not going to get too much into the model equation. That's the kind of technical details that we'll cover in Stat 507. But there does exist this model equation. It's essentially this model equation. It really is like the heart of like generating like probabilities, for example. That's going to be one of our ultimate goals. Like figuring out like what is the probability that an applicant is going to default on a loan, right, based on these variables in our model. And calculating that probability essentially comes from this equation. It works pretty much like our Stat 512 equation. What's a little different is what's on the left-hand side of the equation, and that's part of why I'm a little hesitant to get too deep into it right now. There's also some odds ratios estimates. Odds ratios are something that's used a lot in like the medical context, epidemiology, healthcare. Talks about odds and odds ratios a lot. Logistic regression is kind of like designed to analyze and present odds ratios. It's something we'll talk about. Oh man, to a nauseating degree in Stat 507. It's not really relevant in our current context, so I'm going to gloss over it. The one extra little piece of information I will point out is that very last box in the bottom right, there's something called C. And that's called the C statistic. It's sometimes reported, maybe by other software programs, as the area under the curve, the AUC. And again, it's a bit technical. It would take me like an hour or so to really be able to kind of motivate like what this is and where it's coming from. But it's essentially, it's big picture wise like a measurement of how well our model is performing or working in terms of like classifying people as being good or bad, right? A good loan or a bad loan. We want to judge them as a good person or a bad person. And so it ranges between 0 and 1. Larger is better. I think I have some rules of thumb on the next slide or two. Let's take a look. Let's take a peek. Yeah, so C statistic measures the performance of the model, ranges from 0 to 1. Yeah, so I took this from the textbook Applied Logistic Regression, kind of the Bible of logistic regression. By at least the first two are kind of like I don't know, they're like the rock stars of logistic regression. Hosmer, Libshow, and then at some point, like in a later edition, this Sturdivant person kind of snuck in. But a C of 0.5 means no discrimination. So in some ways, we could think of that as maybe like our lowest value. It's basically saying like our model is like no better than just like flipping a coin and saying like heads, I think this person is like a good credit risk, and tails, I think they're a bad credit risk. Between 0.5 and 0.7 is poor discrimination. Between 0.7 and 0.8 is acceptable. Between 0.8 and 0.9 is excellent. Over 0.9 is outstanding. Man, it's the downside. Can't scroll back without messing up the recording the way I'm doing it. But I think we were 0.6 something. So actually our model is in that poor discrimination range. That said, right, we still have a few steps to like building a better model. Removing some extraneous variables, for example. And then also remember I only worked with like half of the variables in our data set. If I put the other variables in there, I would expect that C statistic is going to get is going to improve. Now, as I foreshadowed, when I talk about like, we haven't really finished building the model, I just kind of gave us like a snapshot for a certain set of variables. For a given set of variables, I can implement any of our Stat 512 model building approaches from an algorithmic perspective inside the prop, right? So one of the more powerful ones is that stepwise forward regression, kind of a blend of forward and backwards regression. So I could implement that in my code. very easily, right? So I same looking code there. Just at the end of the model statement, I put / stepwise, which I think is the same syntax we used in proc GLM. I think it's proc reg that was able to do it, and maybe GLM could not. But the same syntax we used in stat 512. And if I do that stepwise, it'll implement the stepwise process on those variables, right? It's going to basically add them one at a time. So it's going to look at those variables, which variable is the most highly correlated with whether someone pays off their loan, add that into the model. Now, of the remaining variables, which one adds the most above and beyond our first variable? If it's adding a significant amount, put it in the model. Reevaluate everything in the model to see if anything has been rendered non-significant. If it has, remove it from the model, and then keep repeating that process until there's no more, none of the remaining variables add anything significant, and all of the variables in the model are still adding something significant above and beyond their peers. And so you get a lot of output when you do it. Here's just kind of like the final results. So probably something we might have anticipated when we looked at the variable significance in that earlier slide, but this confirms it. It basically says that, right, the three variables that are in our model based off that stepwise regression process is what type of job, how much was the loan for, and how many years have you been at your job. Okay. So of the variables we worked with, which admittedly is only a portion of the variables in our data set, these are the three significant variables. All right, so once I have a model, once I've settled on a model, then like what can I do, or what would I want to do? Well, I can use my model to generate probabilities, and the probabilities in this context are like predicted values. Like in stat 512, we call them predicted values. So predicted values in the context of logistic regression, we think of them as like your estimated probabilities. So these are the estimated probabilities of defaulting. And we calculate them or compute them just like we computed predicted values in stat 512, right? So I run proc logistic. I can put an output statement in there. I can output a whole bunch of different things. In particular, I want to output P. P is the keyword. So I'm going to output those predicted values, those predicted probabilities. I can assign it a name. So the name I assign it is default underscore prob. So default probability of defaulting, being bad on our loan. And then I have to output it to a data set, so I need to name that data set. So I say out equals probabilities. That's just naming the data set. The rest of my code is essentially unchanged. I just, I streamline the model with just the variables that we determined were important. And then I do a proc print on my outputted data set. All right, and so there I have, right, some probabilities of defaulting. So, right, if a person's, if I look at that first line, and if a person's, let's see here, if a person's loan was for 1,100, I mean, probably that's like 1,100 thousands of dollars or something like that. 1,100. If their job was other and they've been at their job for 10.5 years, then my model says that they have a 29.537% chance of defaulting. Now I know the output's like a little clunky. You know, I could of course use like subsetting statements, right? From stat 511, I could par this thing down, and I would if I was going to hand it off to a colleague or to a boss. But I thought it might have some value to show it this way to you, just so you're not surprised when you do it and your data set looks this way. SAS includes all the variables in this data set, even the ones that were not used in the model. So be careful, right? Like it reports like the things like the CL age, like I think that's the age of like their credit limit, or credit line. So it's reported for the first person that was 94.37, but that 94.37 was not in any way used in our model, and it is not in any way impacting that default probability. That default probability is only being constructed with the variables in our model, and the variables in our model were loan and job and the years on the job, YAJ. Okay? Yeah, so we have predicted the probability that someone with a set of attributes will default on a loan. We do need to keep in mind, particularly when I have like continuous variables like the loan amount, that, right, it's conceivable that like my new applicant that I'm trying to make a decision regarding has or wants a loan amount that's different than anything in my data set. Right? So it is possible that like a set of predictor variables is not represented in my data set. And again, it's not a huge deal. We know in stat 512 it's that same solution. We just append an extra observation to the data set that has all the explanatory variables we want to predict for. We set that y variable set to missing, so it's not used to build our model. But then when I output those probabilities, it will use my model equation to generate like an estimated default probability. So same as stat 512. So it has those same limitations, but based on those limitations, right, we can come up with some probability. Right? It should be noted. It maybe feels like we're done. Put a lot of work in up to this point. So it might feel like we're done, but we're really not, right? Because at the end of the day, like our decision is like approve, not approve. Like again, like we're using this like in an action-oriented context. We want to make a decision. So yeah, I get that probability, that 29%, but I still need to like make like an additional step and say like, okay, does like a 29% means that I approve it, or does it mean I don't approve it? Right? It's a deep discussion, a little deeper than I want to get into for just this introductory lecture. Right? From a naive perspective, we might consider giving a loan if that probability is less than 50. So I mean, there's like a certain amount of intuition to like 50-50. But we can show that that's often not like mathematically optimal. That is, like we can sort of prove mathematically there might be better threshold criteria than 50%. And then also just like, just like in the context of the problem, like what we're modeling actually means. Like having like a 50% chance to like not pay you back, like seems like a pretty high probability, doesn't it? Especially if we're loaning out, say, millions of dollars. And so in that case, right, probably a 50% threshold is probably way too high. Maybe, right, we only want, right, our 10% of our customers to default, or 5% of our customers to default. So we would lower that percentage, right, to maybe 10 or 5, for example. And also keep in mind, right, because there's a lot going on here. Most of us have not even seen logistic regression, so that alone is like a pretty big thing that I'm throwing at you. So I have, of course, sort of I don't want to say dumb down the process. I've streamlined it to focus on like the big pictures, the important points of that process. But right, all of our other sort of earlier considerations still matter. There are diagnostics I should be applying to my model. I should have been using this is a huge thing in business applications and in the banking industry, right? This idea of validating your model may be like the most important step. So we would need to have created a holdout data set that we could use to validate our model. Right? All of these things are still important, right? All those principles of good model building that we talked about in Stat 512, they generalize beyond our multiple linear regression model to our logistic regression model and beyond. All right, so that's like a first pass at kind of like, you know, the key idea of how we can basically take historical data of previous loans that we've seen, whether or not the person paid them back, and extract from that historical data enough information to help us decide in a smart, statistically shrewd way whether or not we should approve the loan of a new applicant. And that is the heart of the process. But as you might imagine, in this billion dollar industry, where we have so much money on the line in terms of making the right or the wrong decision, in this day and age where we have like so much computational power, so much statistical knowledge, like in application, it's quite a bit deeper than this. Now, a lot of these kind of extra little auxiliary steps, unfortunately, are just not very well documented. They're not. It's not really. I've looked everywhere. I've wasted so much money, like buying textbooks, and for the most part, they're poorly written. You know, maybe they have typos. Maybe they're just, you know, written by someone who's not an educator, and because of that, they're not good at like getting the point across. I think a lot of times you're dealing with these kind of almost like proprietary processes, and so people, you know, kind of skirt around that by being vague, but they end up being so vague that it's not particularly useful. But I have over the years been able to kind of extract at least like kind of like a big picture of the secondary process. And then, you know, I think it's enough to get you in the door, and then once you're in the door, you know, now you'll be working with your team, and they can kind of walk you through how your particular bank or your particular industry is going to handle some of these things that we're going to talk about now. So the key idea, and one of the terms that you hear a lot in banking, one of the things you'll probably see a lot like in a job description, is this idea of scoring or building a scorecard. So modern day approaches use historical data, so it's what we were doing before, but the goal isn't to like build the model, the goal is to build something called a scorecard. The scorecard is then used to assign a score to an applicant. And then finally, this score is used to make a decision regarding the loan. So I have like an example of a scorecard at the end of this lecture, right? But the basic idea is we take like every attribute in our data set or every attribute in our application, and we assign it like a value, right? So if you're between 20 and 30, right, we maybe give you like say 100 points. If you've been at your job for like 20 years, maybe we give you 200 points, right? Or we add 200 to your score. And so we go through everything, and of course you can, let's leave it at that. But you know, you go through all these attributes and you keep adding together all these scores, and then you get like a final overall score. right? Which is, I mean, we see it all the time. It's like our credit score. It's like our FICO score. These are the idea of like a FICO score is exactly the kind of process that's being used. You know, and of course, banks could use like pre-existing FICO scores, and for smaller banks, perhaps some do. But you know, they also there's a lot of value in them building their own scorecard in-house, right? Using their own sort of secret proprietary techniques, their own data, for example, will make like their decisions more specialized to their case, whereas the FICO score is right a little bit more of like a generalized measurement. So I'm going to kind of walk us through. In the last time I went into kind of a lot of detail. I showed a lot of procs and codes and output. Here I'm going to talk a little bit more big picture about how we can extend that process. You know, the first step is we need to figure out which variables we want to work with, right? This data set's large, but still compared to like the amount of data that like big banks have, it's just a drop in the bucket. Now, right, the process does simplify, right? Like there are regulations out there, and the regulations out there, they dictate a lot of stuff. In fact, most of this process is built around these like these modern day credit loan banking regulations. But of course, one of those is we don't want to be discriminatory in our loaning practices. And so we should not be making decisions based on whether the person is male or female, for example. We shouldn't be making decisions based upon the person's race. And so those variables, even though we probably do have access to that information, they are not variables that should go into our model, right? So we need to review, right, all the regulations and make sure that there's no variables in there, you know, that we should not be using because of potential discriminatory purposes. You know, we might also do some other things. We might look at correlations. You know, we still want to take, like, for example, things like collinearity into account. So if I just look at like at pairwise correlations, it's just kind of like a first step. You know, maybe that'll help me eliminate some variables. I can also decide ahead of time, maybe some variables are known historically not to be important. Maybe some variables are known historically to be important, right? All of this kind of feeds into kind of this first step, right? I start with like a data set that has thousands of variables, and right, maybe I take a little bit of time and maybe I pare that down to hundreds of variables. Right, the next thing I would do, as foreshadowed, I would split that data. In the credit industry, I see a lot this idea of like a 70-30 split, which is similar. I think in 512 I said that I like doing like 1/3, 2/3. So right, those are pretty similar proportions. So split our data so that we can validate it, you know, come up with a test data set that might have 70% of our data, a holdout data set that contains 30% of our data, and then we can use that 30% to test our model. All right, so here is where like things maybe get like a little bit, I don't want to say crazy, but just, I don't know, a little bit off the rails from like what we've seen in previous classes. But this is extremely common practice in the credit industry, and that is like, all right, we've decided on the variables we want to work with. We still haven't like, you know, like tried to build a model. We haven't really funneled them through ProcLogistic. So I kind of have this kind of like initial set of variables. And the next thing I do is I apply what's called a weight of evidence transformation to the variables. And then we'll see I can use this weight of evidence transformation to compute something called the information value, the IV, of all of my variables. This is a really laborious and time-consuming task. So this is like this kind of like pre-processing step. We haven't even gotten into model building, but like this is sort of like getting our data ready for the model building, and it's very difficult to do for a number of reasons, which I'll go into over the next few slides. But this idea of a weight of evidence transformation is we're essentially taking our data and we're like, the terminology that's used a lot in the industry is we're breaking it into bins. You could think of bins as just like categories. So we're essentially we're creating categorical variables, right? So we're taking something that's numerical, something that's continuous, something like age, for example, and we're taking that age variable and we're binning it. We're putting each person into a bin / category. So like intuitively, we would think of age as like, oh, you could be in your 20s, you could be in your 30s, you could be in your 40s, you could be in your 50s, right? That's like an intuitive way of doing it. We're going to create our bins from a purely like mathematical perspective. So, right, our bins might be something weird like 21 to 32, and then 33 to 37, and then 38 to like 59. Like our bins are going to be made based on these sort of statistical optimality criteria, some of which I'll talk about in a future slide. So most of the work is when we have numeric variables. But even our categorical variables might need a little bit of work as well. We're generally not creating new categories, but we might need to lump some categories together. We might need to like collapse some categories. So maybe if my categorical variable has like 20 or 30 outcomes, you know, like if I measure a person's job very precisely, there's like hundreds of jobs. But I might need to bin those together. I might need to collapse some of those jobs so I go from say 200 categories to like 20 categories, or right in our case, right, we actually we broke the jobs into basically 6 categories. So most of the work on numeric variables, sometimes we also do have to kind of tweak categorical variables as well. So that's like that first step, is we're going to find the bins. And then for every observation in the bin, we're going to give it a certain score. Okay, so let's see, let's look at the next slide. Yeah, so here's the certain score. So the weight of evidence calculation is the log odds. So the log of the percent of good customers over the percent of bad customers for that specific bin, right? So I'm going to calculate this formula for every one of my bins. Excuse me. So think of our age category, for example. And let's say that it did just happen by convenience to break into like the 20s and the 30s, and you're in your 40s, you're in your 50s. So what am I basically doing? I'm looking at everyone who's in the 20s age category, who's age 20 through 29. I'm looking at now just these people. And for these people, what percent of them were good, like what percent of them paid back their loan, and I contrast that, I divide that by, right, what percent of them are bad, right? So I have my percent good over percent bad, right? So I can see like conceptually, right, this measurement is saying like how well does this particular category discriminate between my categories of interest, good or bad, pay back the loan, don't pay back the loan. Right, the larger that ratio, the sort of better the discrimination. Or it's smaller too, right? I guess the farther that ratio is from 1. Right? And the log of 1, remember, is 0. So the farther that ratio is from 1, right, the sort of better like this category does in terms of like discriminating, which is nice information to have, right? So it's something that we don't always have just based off like a model equation, for example, or like, remember, a variable's p-value, because the p-value, it can measure effect size, but remember, a p-value also can measure sample size. And so this is robust to that idea of sample size, which is part of what makes it attractive. It's also on this log scale, which we didn't really get into a lot of the details in logistic regression. We will eventually apply logistic regression, and logistic regression is on a log scale. So we've kind of standardized the scales. But the idea is, like, I create that ratio for all my historical data of people in their 20s. And now, instead of like the age, so instead of like my data set saying like this person's 23 and this person's 27 and this person's 21, now everyone who's in their 20s has the same score. And that score is the log of the percent of good over the percent of bad. Okay? So if I've made, say, I don't know, 7 age bins, then now there's only 7 possibilities for my transformed age variable. 1 for each bin. Yeah, and looking at that ratio, right, we can see intuitively a positive weight of evidence means that the proportion of good customers is more than bad customers, and vice versa if it's negative, right? Negative means the percent of bad is more. Again, like from a credit perspective and people defaulting, you know, we tend to see people defaulting less frequently. So we're generally working with you know, positive numbers. So here are some like pretty widely held sort of standard conventions. Each bin should have at least 5% of the observation, so you want a decent amount of information in every bin. Each bin should be non-zero for both good and bad loans, so you want to make sure that there's, right, at least one person who defaulted and one person who didn't default in every bin. The weight of evidence should be distinct for each category, right? So if 2 bins have weight of evidence scores that are very close to one another, we should just combine them together. The weight of evidence should be monotonic, so that means that it should be always increasing as I move through my age category, from my 20s to my 30s to my 40s to my 50s to my 60s. I want to see that weight of evidence score either always getting larger or always getting smaller. And then one cool thing, one of the many advantages of this process is that we could actually take missing values and just think of missing values as their own category. And that allows us to assess like whether missing values, for example, actually maybe have some sort of predictive power in terms of whether or not someone will default. So we can just think of missing values as their own bin. We could also, incidentally, like, another advantage of this is like also outliers get kind of like collapsed into bins as well. And so it kind of helps us deal with outliers as well as missing values. So I have a weight of evidence value for every category. So like if my age thing had 7 categories, I have 7 weight of evidence values. I can combine those 7 weight of evidence values into a single measurement for the variable age. And that's this information value. So the information value is essentially just summing up the weight of evidences for each category. So in our age example, we'd be adding up the 7 weight of evidences weighted by the difference in percent good and bad. And then here's some rules of thumb. for what are some good information value numbers to look at. Less than 0.02 is not going to be useful. Between 0.02 and 0.1 is weak predictive power. Between 0.1 and 0.3 is medium predictive power. Between 0.3 and 0.5 strong predictive power. More than 0.5 is like sort of like suspiciously strong, like maybe there's something weird going on in your data. Like maybe like you're using some variable to predict like default that like you wouldn't actually know. Like it's almost like like you're using like whether or not someone defaults to predict whether they're going to default, something along those lines. So typically it means there's some kind of weird flaw. You should be a little bit critical of your model, which is cool, right? We don't see like rules of thumb like that very often. This idea of it's like almost too perfect. Yeah, so some advantages of this whole like binning process, weight of evidence process, information value process, right? It puts all of our independent variables on the same scale, right? So sometimes when I'm trying to like, if I build a model equation and I try to use the idea like this coefficient is larger than that coefficient, so I think that variable is like more meaningful. That's not always true because a lot of times, at least like in our 512 work, like the coefficient is like based on like what's being measured, right? So if it's an attribute that takes large values, then it's going to have a large coefficient. If it's a variable that takes very small values, it's going to have a small coefficient. So the coefficient is less reflecting like how important that variable is, and more reflecting just like the range of the variable that's being used for that coefficient. So the problem is you're like comparing apples and oranges. But the idea, right, one of the advantages of doing this weight of evidence transformation is it sort of turns everything into an apple. Now everything is on the same scale. And so now I can make these sort of cross comparisons in a meaningful way. As I alluded to earlier, it's a measurement of predictive power different from a p-value that has some advantages, some disadvantages. But right, it is a big advantage when we're trying to use it as a measurement of effect size. Because remember, the p-value is a measurement of significance. And significance doesn't always mean effect size. Significance sometimes just means you have a big data set. We also talked about how this process, this weight of evidence process, allows us to handle missing data and outliers in a pretty cool way. And even though it's difficult, it is a lot of work to come up with like a binning process that like satisfies all those conventions. Once we've done that work, it does allow us to build this like scorecard, which is very intuitive in its utility and how it's used. And part of that idea of its ease of use, its transparency, is that is also like a regulatory feature, because we're also having to deal with these legal constraints when we're building these models. And part of those legal constraints is we need to be able to clearly articulate why one person was not given a loan and why a different person was given a loan. And this kind of pre-process sort of sets us up to be able to do that. Now, I would love to show this to you, this process, but again, similar to like decision trees, it's just not doable in it's just not doable in SAS, unfortunately, not base SAS, right? The SAS add-on, SAS Enterprise Miner, can actually do this very easily, very powerfully. Enterprise Miner is sort of tailor-made for doing this type of stuff. It's also pretty awkward to do it in R. You got to kind of download different packages and different bits and pieces kind of collected from various ways. So like just kind of like doing it with just kind of like publicly available software, like it's university available software, is unfortunately just not that realistic with kind of what we were provided. Now, one thing we can do in base SAS, though, is we can play around with this binning process, right? That weight of evidence process that I was talking about, using something called proc HP bin. So HP just means like high performance, I think. So there's certain newer procs in SAS that are made for like higher level types of computing. So they have an HP in front of them. But right, you can almost think of it as like proc bin. It's just like a high performing proc bin. Here's just like a little bit of like just kind of some playing around code to give you a sense that it is pretty tough to do, particularly with base SAS. There are more bells and whistles in terms of doing this in the enterprise miner. But so proc HP bin, I can specify ahead of time how many bins I want. So 10 is like a pretty common like starting number. And so here I just wanted to focus on my numerical variable. So I put years on job and loan amount. I create this like ODS output thing called a mapping. So my bin is going to essentially create those bins, and then it's going to output what the bins are. I can then take the bins that were determined the first time I ran HP bin, and I can plug them into a second instance of HP bin. So the second instance is basically I'm going to say take those bins and compute the weight of evidence and compute the information value. Okay. So let's take a look at the output here. So here's like some of the output. You can see it took the loan variable and it created 10 bins. So if you count those lines, there should be 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Phew. It tells me what the bin is, right? So the bin is, first one is less than 9980. The other one is between 9980 and 18860, right? It builds these bins based on these kind of like these default criteria that I can tweak and play around with. It also tells me like what percent of the data falls in each bin. And notice that some of these bins actually I think 6 of these bins violate our rule where we say we want at least 5% of the data in there. So I've probably made too many bins. I should rerun at least this variable, right? With maybe like, I mean, I see 4. Maybe I'll try like 6 or something and see if that does a better job. So again, I'm just kind of showing an example, but these bins are not, this is a bad set of bins that SAS has made for me. And that's why I said like this is a pretty time-consuming process, because like it takes like a lot of trial and error to sort of come up with the bins that satisfy all these different criteria. So this is like that first instance of HP bin where it creates the bins. Here's some sample output from the second instance where it creates the weight of evidence. The weight of evidence, I believe, is that second column. So one thing I can observe is my weight of evidence, like my bins are giving me a bad weight of evidence, because the weight of evidence, if I look at that, the years on job bins, it goes negative 0.22 to positive 0.05 to negative 0.02 to negative 0.05 to negative 0.127 to positive 0.6977. That is not monotonic. So I'm also violating that convention as well. That's also an indicator that I need to work with smaller bins. 10 is too many for this particular set of data. And then finally, I actually get like an output of the information value based on these sets of bins. And I forget exactly what that criteria was. I think this fell into like weak predictive power. anything between like 0.01 and 0.10 was, I think, weak predictive power. But also keep in mind, like these are demonstratively bad bends. If you were to play around with this, and I leave it to you to do that as maybe like an unofficial lab exercise, is try rerunning this. The data set's posted on D2L. Try running this with just 5 bins and see how much that improves the information value. See if that will get us 5% in each category. See if that'll make our weight of evidence monotonic. Okay, so I'll kind of end here with the invitation to you to stop just sort of sitting there passively and to instead, right, be active and to actually start playing around with this data yourself a little bit. Yeah. All right, so here we go. Conclusions. Loan had that information value of 0.10. Years on job had that information value of 0.08. That means, okay, so I did put it here, they have between weak to medium weak predicted power. But again, we should keep in mind, like these are bad bends, so I would expect their power, their information value to be low. So the next step, right? This is a big step, but we're still kind of just like getting started, right? We can use that information value to filter out some more variables, and now we've basically settled on our candidate variables. We now will run them through proc logistic, but on their weight of evidence scale. We then get like the coefficients from our model equation, and we apply like a certain set of formulas to these model equation coefficients that we can use to build our scorecard, right? That's our end goal, is this scorecard. I've read a lot of books on this. You know, if you find yourself in a job where this is something you need to do, this is one of the better books I've seen in terms of kind of walking you through the actual formula used to build the scorecard. It's a bit much for this introductory lecture, but there's a reference if you want to go a little deeper. Yeah, and so here's kind of like an example scorecard, right? So if someone was in the first age category between 0 and 30, you know, we would assign them 80 points. Right, it looks like, here's that monotonic idea, it looks like in general, like older people are sort of more likely to pay back their loans, right? So the older you are, you know, the better your score. Not surprisingly, income also monotonic. The more money you're making, the larger your score is going to be. Employed, yes or no. Obviously being employed is better than not being employed. Right, you do have this sort of base amount, so it's not necessarily a negative. It's just, you can think of that 100 as kind of like an intercept in a way. That 100 is kind of like this baseline value, and that 140 is kind of like saying like this much extra is being added on because you're employed. And you know, we would have more variables, but for any one person, we'd say, okay, like you're between 0 and 30, you're making between 1,000, whatever that is, a month, a paycheck, and you're not employed, so your score is 80 plus 5 plus 100, your score is 185, and that's either going to be more or less than, right, our cutoff. Yeah, so we compare this score to a cutoff value to determine whether or not to apply the loan. We can determine the cutoff by analyzing the ROC curve. So the ROC curve, remember I went back to that C statistic, which I said is like area under the curve. The curve I'm referring to when I say area under the curve is referred to as the ROC curve. It's a bit technical. We will talk about it in a lot of detail in Stat 507. There are like these ways, this Yoden's J statistic being one of them, that you can sort of analyze the curve to kind of come up with this like mathematically, statistically optimal sort of cutoff point. But we need a deeper knowledge of logistic regression to sort of be able to do that. So I'm going to leave that here for now. Who knows, maybe when I teach you in the fall, if you ask me, maybe I can do a little bonus lecture then in terms of how we might use this J statistic to generate some cutoff points. All right. So I believe this is the last slide. I believe this wraps up our credit risk analytics. You know, a lot of information there. Some of it very, very specific, some of it pretty big picture, kind of like a mix of the two. And hopefully it ends up being useful to you. I'm sure it will if you end up deciding to go the route of working in banking or credit analytics. Bye for now.